Hello, everybody, and welcome to your Chem 113 review on predicting ion charges. My name is Jason, and I work for the ASU Tutoring Centers. Now, before we get into the actual question, let's first kind of go over what's exactly happening with ions. Why do ions form? Well, as we'll discuss in future videos, electrons that quote-unquote orbit around the center of your atom, around the nucleus of your atom, they fill up in these things called shells. So they tend to fill up in the shells closest to the nucleus first, and then they sort of fill up in the outer shells as you go. Those electrons in the very outer shells are called valence electrons. Valence electrons. They're the ones in the very outer shell of your atom, and they are the ones that participate in chemical reactions. So they are, in some regard, the most important electrons for your element. They are the ones that will actually be bonding with other electrons, with other atoms to form these bonds, okay? They're the ones that participate in chemical reactions. Now, this over here, I have a periodic table for a reason. This column over here, these elements are all called noble gases. And noble gases are very happy. They tend to not form bonds because they have what we call a full octet, which means in their very outer shell, they have all 8 valence electrons. Okay, pretty much 8 valence electrons is what you want to get. If you have 8 valence electrons, you're happy. No bonding is going to be happening really. There can be bonding. There are certain cases, especially with like xenon. But traditionally, noble gases are very stable, very happy. They have all 8 of their valence electrons. They don't need to do anything. The goal of all of the other elements on the periodic table is to get a full octet somehow. Okay? So when we go through the columns pretty much tell us how many valence electrons we have in our outer shell. So see how this has like a 1A and a 2A? And then over here, 3A, 4A, 5, 6, and 7A. Those numbers tell you how many valence electrons you have. You have 1 valence electron here, 2 there, 3, 4, 5, 6, 7. And I know you're thinking, well, what about all this stuff in here? Those are called the transition metals, and they are, they're weird. And we will talk about them in later videos. So don't worry about them for now. So we're really going to be talking about all these other ones out here. So they tell us how many valence electrons we have. So for instance, in this first column, we only have 1 valence electron. So if our goal is to get all 8, we can either add 7 electrons, or we have another option. What if we just get rid of that valence electron in the outer shell? Pretty much bump it back. We get rid of that valence electron, and we essentially get rid of that entire outer shell, right? Because if there's only 1 electron and we get rid of it, that outer shell no longer has any electrons in it. And so we kind of get rid of that outer shell and we go back inside to the next inner shell, and that next inner shell must have already been filled. The only way for us to get to that very outer shell is if the inner one was already filled. So in fact, another way we can get a full octet is instead of adding 7 electrons, what if instead we just remove 1? So what'll be easier, adding 7 or removing just 1? Probably just removing 1, right? So typically, the elements in this first column, what they'll do is they'll remove an electron. And in doing so, they will have a full octet. They'll be very happy. But what happens when they remove an electron? Well, they're removing a negative charge, so their charge is probably going to be a +1. So everything in your first column will tend to form a charge of +1. Similarly, the second column will form +2, and the third column will form +3. Go ahead and erase this stuff here. The third column will form a charge of +3. Now we're going to skip over the fourth column real quick. Let's go to the fifth column. So the fifth column has a couple options. You can either add 1, 2, 3. You can add 3 electrons, or you can remove 5. Which is going to be easiest? Probably just adding the 3, right? Instead of having to remove a whole 5. So once we get to the fifth column, these atoms tend to add electrons. So this column here, the 5a column, will tend to add 3 electrons, giving it an overall charge of -3. And then similarly, -2 and -1. Now, what about this fourth column? Because it can either add 4 or remove 4 electrons. There's 2 options, and they both seem pretty equal. Well, the fourth column tends to not form ions. We tend to not get many carbon or silicon ions. And we'll talk about that in the future. We'll talk about covalent bonds. Carbons and silicons and all the ones below it tend to form covalent bonds instead of ionic bonds. So they tend to not form ions, so we're not even going to worry about this fourth column. Don't even worry about it. Okay, so if we're looking at barium, let's see, where's barium? Try to find it. We're looking for Ba, correct? Barium is right down here. So what column is it in? It's in the 2a column. That means the most stable ion, the ion that's most likely to occur for barium is going to be a +2. So barium, you are likely going to get Ba with a 2+. Okay, now let's look for oxygen. Where's oxygen at? Oxygen is over here. It's in the 6th column, which means it's most likely to get a -2 charge. So oxygen is most likely to have O2-. Okay. So the most stable ion that an element is likely to form depends on what column it is in. Okay, and I have all of the common columns listed right there. Their charges for those columns listed right there. Awesome. Thank you all for watching. As I mentioned at the beginning, I work for the ASU tutoring centers. If you want more information about the free resources we have on all 4 major ASU campuses and online, please check out tutoring.asu.edu. If you want to see more videos like this one that go over specific concepts from your course, or maybe you want to see what upcoming review sessions we have for the exams in your course, please check out this link below. Thank you again for watching, and I hope you have an amazing day.